Today we're going over Chapter 19, Estimating with Confidence. We're going back to our example from Chapter 18, the one with the pig tosses with trotters and razorbacks. So our population is all pig tosses, our parameters, the true proportion of razorbacks, our sample is 100 pig tosses, and our test statistic for the 100 pig tosses was 0.16, 16 out of 100. So based on one sample, we can't conclude what the true proportion of razorbacks is. However, we can come up with an interval that might contain that true portion of razorbacks. What we're going to do is we're going to tell you the interval, but we're also going to state how confident we are the true proportion falls within that interval. So always check your conditions necessary to use the normal model for proportions. So you always have to do this, even if it's not stated. So you have to state that this is a random sample of pig tosses. We have to use the 10% condition, state in 100 pig tosses is less than 10% of all possible tosses. And then our success and failure, stating that it's large enough. So n times p hat is 16, which is greater than 10, and n times q hat is 84, which is greater than 10. Our confidence interval, the formula for that is the statistic plus or minus the critical value times the standard error. And then we also give it as an interval, the lower value, than the upper value. Every single time you do this, you want to write the formula down. You get credit for writing the formula down just as you do with the test statistic for a hypothesis test. So typical confidence levels that we use are 90%, which has a critical value of 1.645. So this Z star is your critical value. And you can find this using your calculator or the table. We'll go over in class how to use the table to find Z star. So when you have a 90% one, it's 1.645, 95% confidence interval, 1.96, and 99% confidence interval is 2.576. Now, these are typically the three that we tell you to memorize because they are used often. What the sketch looks like for a 90% confidence interval, so from here to here is your 90%, which means on either side here, this is 5%, and this area on this side is 5%. And here we have this line would be negative Z star. This would be positive Z star. Okay, and how we find Z star using our calculator, it would be INV norm, which is under distribution, which is second in the VARS key, of 0.95, because it's 95%, so we're counting the area going from the left, so it's this entire area, 90 plus this 5% here, and that would give you your 1.645. When we're talking about a 95% confidence interval, and zeros here, so we have 0 here, 95% confidence interval means this is 95% of the area, which means this little area here is 2.5%, and this little area here is 2.5%. So we have a negative Z star here and Z star here. Remember, we're finding the area from Z star all the way measuring from the left. So Z star here would be inverse norm 0.975. And that would give you 1.96. And then the last one, when we have a 99% confidence interval, this area in the middle is 99%. We have negative Z star here, Z star here. So my area in here would just be 0.5%. And this area on this side would be 0.5%. So to find Z star, it's from here all the way back. That would be 99.5%. So it would be inverse norm of 0.995, which would give you 2.576. So those are ones that we typically use. So what I want to do is I want to construct a 95% confidence interval for the true proportion of razorbacks from my example. So the first thing we need to do is, since it's a 95% confidence interval, we already know that our Z star equals 1.96. Okay. And then we know that our formula is P hat. So we're using, it's best just to use this formula here, P hat plus or minus Z star times the square root of PQ all over N. So you go ahead and you plug your values in. So P hat is 0.16 plus or minus Z star is 1.96. Since we don't have PQ, it should be P hat Q hat. So this would be 0.16 times 0.84. Our N for this example was 100 tosses. And then you would get 0.16 plus or minus 0.0719. And our interval would be 0.088 to 0.232. So you would state, and this is the sentence stem you would use, I am 95% confident that the true population proportion of razorbacks, so whatever your example talks about, lies within the interval of 0.088 and 0.232. And as we go through more examples, you'll see how you can interpret your confidence interval using the same stem, but just tweaked a little bit here and there. So caution, do not say any of the following. There is a 95% chance that the true proportion of razorbacks falls within this interval. Or I am 95% confident that P hat is within this interval. Or in a 95% of all samples, the true proportion of razorbacks is within this interval. When we have a higher confidence level, that means a higher percentage of all samples produce intervals that contain the true value of the parameter. Therefore, we want a high level of confidence. A smaller margin of error allows us to get closer to the true value of the parameter, so that would give us a smaller interval width. So we also want a small margin of error. So how do we get, or how do we reduce the margin of error? So there's a couple of ways that we can reduce the margin of error. First, we can have a lower confidence interval. So to get a lower confidence interval, we decrease Z star. So CI is for confidence interval. A lower standard deviation, so SD is standard deviation. Increase sample size. To cut the margin of error in half, we must increase the sample size found at least 4 times. So if you want to cut the margin of error in half, you have to increase the sample size by 4 times. To determine the sample size n that will yield a specific margin of error, m, set the expression for the margin of error equal to m and then solve for n. Always round n up to the next greatest integer. So that, what we're talking about, margin of error equals Z star times the square root of P hat Q hat all over n. And here we want to solve for n. Just use caution because the margin of error only covers random sample and errors. Things like undercoverage, non-response, and poor sample and designs can cause additional errors.